Welcome back, everyone. So let's just finish the proof of the sensitivity conjecture, or theorem now. So before I told you about this, this sign adjacency matrix for the n-dimensional hypercube is defined recursively as this. For the one-dimensional one, it's not the identity 0, 1, 1, 0. And then if you have such matrix for Bn minus 1, you can make one for Bn just by putting a block here, minus Bn minus 1 here, and identity. And the exercise, basically, if Bn minus 1 square equals n minus 1 identity of the appropriate order, you can square Bn, and you can get n times the identity. Okay, and from there you can calculate the eigenvalues are square root of n and minus square root of n, and they have to have the same multiplicity. Okay. Yeah. All right. So now, this was, I think, so in the first step was so there is a signed adjacency matrix. Let's call it Bn. Of the cube Qn such that Bn square is n times I to n, or Bn has eigenvalues square root of n and minus square root of n. Okay. Now the second step in this proof was was Cauchy interlacing. I mean, you can do it with bare hands without using this interlacing, but it's the easiest thing for me to tell you about is with Cauchy interlacing, and is as follows. So I will apply, remember, like the Cauchy interlacing theorem was true for any real and symmetric matrix. In most of the cases for us, we applied it for adjacency matrix, but I can apply it for a sign adjacency matrix. So this sign adjacency matrix is like a adjacency matrix, but some of the ones have been changed to minus ones, such that the matrix is symmetric. Okay? So you have here gamma, your graph. So you have, so the graph Qn has 2 to the n vertices, and the graph gamma has 2 to the n minus 1 plus 1 vertices. So if you apply here Cauchy interlacing, what you will get is, so for this Qn, we'll apply it for the matrix Bn. So the matrix Bn will have square root of n eigenvalue with multiplicity 2 to the n minus 1, and you will have here minus square root of n with multiplicity with the same multiplicity 2 to the n minus 1. Okay. So if you apply here, you will get that the largest eigenvalue of gamma, because it has these many vertices, is going to be greater or equal. Remember that we had this in our eigenvalue inequalities. We had something that mu I, I forget, it was like mu I, is less than or equal than theta I is greater or equal than theta I plus n minus n. Remember this part. Now we will use this part here, and you put, you will put I will be 1, and here this will be lambda. You do the calculation, this n will be 2 to the n, this m will be 2 to the n minus 1 plus 1, and with the I, so this will become actually lambda 2 to the n minus 1 of Bn. Okay? This quantity here, so I is 1, this n for us is 2 to the n, and m is 2 to the n minus 1 plus 1. So when you do that calculation, you'll get exactly lambda 2 to the n minus 1. So the 2 to the n minus 1 largest eigenvalue. But that one is exactly like this one hits it right on the brink, because this will be square root of n. Hey? Yes. So what you do, you take, so very good question. So what you have this matrix Bn for the cube Qn, and let's say gamma is here, a bit more than a half. You just take the principal sum matrix of that. So this one is also plus minus 1, 0. So here it's Cauchy interlacing, but Cauchy interlacing for the usual adjacency matrix doesn't give you anything useful. But this matrix because the spectrum has compressed to square root of n and minus square root of n, this matrix magically works.
In that case, submatrix will having this one, right?
Yeah, so this is so for gamma you will have the submatrix corresponding to the principal submatrix of Bn, and for that submatrix this is not of the adjacency matrix. Let me be more precise. It will be lambda 1 of, let's say, AS of gamma. It will be like a sign adjacency matrix of gamma. Very good. That's a very good point. Okay. And then, so that's step 2 in this Cauchy interlacing. And then, question?
That's the submatrix of Bn, right?
Yes. So you just keep the vertices and the rows and columns corresponding to gamma. And because the numbers work exactly, that you get here 2n minus 1. Cauchy interlacing gives you that lambda 1 of this sign adjacency matrix of gamma is greater or equal than square root of n. And the third step is that we proved, where I ask you to prove that the maximum degree of a graph is always greater or equal than lambda 1 of the adjacency matrix. You can prove that it's also greater or equal to largest eigenvalue of any sign adjacency matrix by the same type of argument. I think we did the proof. And if you use that proof, it works for any sign adjacency matrix of gamma. So there is a sign adjacency matrix like this. That's where kind of the magic happens. Cauchy interlacing, the largest eigenvalue of that sign adjacency matrix is at least square root of n. This is known. Maximum degree always beats largest eigenvalue. So maximum degree will be at least square root of n. Okay. So that's this proof. And again, before he obtained square root of n, the best bound that people had was log of n. And this square root of n, people proved before that this would be best possible. So there are some subsets that you can pick that this works for, obviously for n a perfect square. Okay. So that's that. So what I'll do for the remaining time now, I will tell you the equivalence between this notion of sign adjacency matrix and the notion of a two-cover of a graph, because that will come into play tomorrow when I'll tell you a little bit about expander graphs and so on. So for now, I'll talk a little bit more about this notion of sign adjacency matrix and how it relates to something else. So, sign so I can put here like an equivalent. They're going to be equivalent to something called two covers. Okay, in the following sense, here we'll have matrices, here two covers will be graphs, but I'll explain what I mean by this. Okay, first, let me give you a definition of a two-lift or a two-cover of a graph. So, and I'll do the general definition, I'll do an example. So let me give you here you have gamma, a graph. From it we can construct the following gamma prime would be a two-cover. So for maybe I'll do it this way. So gamma, you'll see in a second while I'll do this picture, gamma prime will be the following graph. You have as vertex set of the graph Cartesian product with 0, 1. So from each vertex from here, I will make two copies of the vertex in the two cover. So I have here, let me say this is my graph. Let's say A, B, C. This is a complete graph. And here I will make in gamma prime, so my gamma is K3. In gamma prime, I will make two copies. I'll make an A0 and an A1 copy. Okay. For B, I will do the same. I'll have B0 and B1, and for C, I'll make another copy, C0 and C1. So let me do it here, B0, A0. Okay, so I want to define what is the double cover, and this will be some edge set. So the vertex set, it doubles, so every vertex here gets 2 copies up here, okay? Now what do you do? For every edge, when you look at these so A has 2 copies here, A0, A1, B has 2 copies, B0, B1, you have 2 choices. You can either add a perfect matching like this, or you can add the other perfect match. There are two perfect matchings between the parts. So here I chose to do this. Here I chose to do this. And here I choose to go do this kind of diagonal form. Okay? So the vertex set is this, and then the edges, if you have, so how I did it here, if X is adjacent to Y, that means that here you have 2 possibilities. Either X0 is adjacent to Y0, X0 is adjacent to Y0, and X1 is adjacent to Y1, or you have X0 adjacent to Y1 and X1 adjacent to Y0. So that's the rule. So you won't have, there isn't just 2 cover. There will be, for each edge you have 2 choices. You either keep the edges parallel or you make a cross. Make sense? So this is called a 2 cover. Now, why is it called a 2 cover? I kind of draw them like this so that I show you why is it a cover. So what happens is there is a function f from the vertex set of this 2 cover to the vertex set of the graph itself. And this function will take f of x0 will equal f of x1 will equal x. So basically these two vertices, I map them into A0, A1, I map into A, B0, B1, I map it to B, so it's kind of like they're covering in that sense. And what is this function? So this function is, f is a graph homomorphism, which is something that I haven't defined, but graph homomorphism, what it means that it maps edges to edges. In our graph, like if I have, so A1 is adjacent to B1, where does A1 go to? Goes to A, B1 goes to B, there's also an edge here. I mean here, everything is an edge, so it's relatively easy, but a graph homomorphism maps edges to edges. You have to make a distinction between graph homomorphism and graph isomorphism. In graph isomorphism, you map edges to edges and you map non-edges to non-edges. So that's kind of the difference, okay? 1. So this is 1. And second, for every vertex in the cover, for every xj, if you take this function f and you restrict it to xj, to the vertex xj, and to its neighborhood, union gamma xj, this function is a graph, it's going to be locally a graph isomorphism. So, for example, if I take the function and I pick A0, and I look at A0, let me see. So, what do I want to say here? Yeah, it's well, it's not a graph isomorphism. This will give you a bijection this set and the image of it. Yeah, it doesn't have to be isomorphism. Okay. For this example, let's just, okay, this is the, I have this example. Now, can you recognize, my drawing is a little bit messy there, but can you recognize what is a graph on the top? Cycle C6. So cycle C6 is a two cover so C6 is a two cover of K3. Obviously, if I have two copies of K3, 2K3 is a two cover of K3. That's also true, because you don't, all the edges are parallel. Something for you to try at home, the cube Q3 is a two cover of K4. So try to see how the cube is a two cover of this cube is a two cover of K4. Okay.
Sorry.
Yes.
Explain the second.
So for the second one, it's kind of locally that. So what happens is locally you'll have a bijection. So you'll have, if I have pick a vertex A1, it has neighbors B1 and C0. There will be a bijective to A, B, C. Okay, so that's what it is. Okay. All right. Now, here's the relation between, if I have a two cover, let me show you how this relates to a sign adjacency matrix of the graph. That's yes.
Small question.
Yeah.
So either you take these two conditions or you take these two conditions, right?
Yeah. But for two cover, this is what I will work with, because this gives me like a concrete way of defining. So basically, I have a choice. So for each edge, you pick some kind of you make some choice if you're going to keep the edges parallel or you're going to cross it. So let's say you have that.
Once, so here in this picture, A0 is connected to C1.
Yes, A0 is, so this edge AC, you decided not to keep the edges parallel, you decided to cross them. Yes, so A0 is connected to C1, A1 is connected to C0. So this gamma prime is one two cover of this graph, and because you do this procedure, it can happen for every edge. Here you have 3 edges, you will have 8 possible two covers. I mean, so they will be isomorphic to each other because you will get sometimes either 2K3 or you get C6. But two cover is not unique. There are many, and if you think about it, sign adjacency matrices also, they're not unique. So this is where the connection is going to be, because for each edge, I choose to have these parallel edges or to have them cross. It will be something similar now for the sign adjacency matrix. I choose to either make the entry in that position to change the ones to -1s. That's going to be the game. So if I have a two cover gamma prime, I'm going to make a sign adjacency matrix AS as follows. So AS will be V by V, but now AX in the position XY will be the following. So I will put a 0 if XY are not adjacent, so those don't interest me. So I have to deal with what happens if XY are adjacent. So if X is adjacent to Y, and in gamma prime, X0 is adjacent to Y0, and X1 is adjacent to Y1, I put a 1. So if I have parallel edges, I just keep a 1. Okay? And you can imagine what happens if X is adjacent to Y and x0 is adjacent to y1, and x1 is adjacent to y0. Then I put a -1. And then otherwise, if there's no edge in xy, so otherwise if x is not adjacent to y, there's no reason to put anything. Okay, so let's do an example here for this. So for K3, for this adjacency matrix of K3, let me label them A, B, C, A, B, C, and you know what it is, 0, 0, 0, 1, 1, 1, 1, 1. Okay, this is the adjacency matrix. Now, the sign adjacency matrix for that picture, so let me. So let me draw that, maybe that picture again here. So this is A0, this is B0, this is C0, this is A1, this is B1, this is C1. Okay? So now, if I look at, so that's a picture of the graph. Now, I want to write here, I will write here the adjacency matrix of gamma prime. Okay, this is going to be a bit big, but I will do it the following. I will do here, I won't write it A, comma 0, I'll just put A0, B0, C0, A1, B1, C1, A0, B0, C0, A1, B1, C1. Okay. So, this is the adjacency matrix of the big graph. I will write it down in a second. But before I do that, what I want to show you here is that the two cover that I have here, what is the sign adjacency matrix that I define? AS of this graph gamma, AS of gamma. It will have the same labeling as A, B, C, A, B, C. I have 0 here. Now, I look at A and B. For A and B, the edges were parallel, so I keep a 1. For B and C, the edges are parallel, so I keep a 1. And for A and C, I decided to cross, so I put a -1. So that's what I mean that this sign adjacency matrix, it's just obtained from this matrix. You pick some entries and you change them to -1, but you have to change them, so it stays symmetric on both sides. People have studied also like something where it's called skew symmetric, in which you change the one only on one side of the diagonal. Okay, but here this matrix stays symmetric because you change the one, like we changed this 1 to -1 on both sides. Okay, but obviously you have -1, so there's no non-negativity or anything. Okay, so what I want to convince you now is that for these two cover, you can recover the adjacent, if you look at this bigger matrix, so the graph, the size of your graph just doubled. And what I claim is that you can get the eigenvalues of here from this matrix by taking the eigenvalues of the original graph and the eigenvalues of the sign adjacency matrix graph. That's what will always happen. So that's why I say that sign adjacency matrices are equivalent to two covers, because if you give me a two cover, this is my sign adjacency matrix. If you give me a sign adjacency matrix, I can represent it by a two cover. Make sense? Yeah.
The sign and this with respect to this two cover.
Yes, with respect to this two cover, yeah. So what I'll try to show you now is why the spectrum of the adjacency matrix of this graph will equal the spectrum of this union the spectrum of this. So this is One way you can do it, so this is not written in many parts as far as I can tell you, but you can already, you have enough, we talked enough about equitable partitions that you can kind of sense there is a connection. So if I have this graph here, the partition into these blobs, does it look like an equitable partition to you? Well, inside these blobs I put nothing, so it's zero regular. And what do I see between every blobs? I either see a perfect matching, in this case there are perfect matchings everywhere, but in other situations you may not see anything, because if there was not an edge in the graph, there wouldn't be an edge here. But either way it would be an equitable partition. What will be the quotient matrix of this partition? In this case, will be the complete graph, will be the adjacency matrix. So in general, the quotient matrix of this partition will be the adjacency matrix of the graph. And that tells you, by using this equitable partition, that this big graph, which is twice the size, inherits the eigenvalues of the original graph. And sometimes these eigenvalues of the graph gamma, they're called the old eigenvalues, because the 2 cover will get the okay? But the 2 cover has twice as many vertices, so you have to have some new eigenvalues, which is the stuff that we talked about with the equitable partition. And you can use this argument, the argument there, to say, okay, how are these, so the eigenvalues from here that appear here will have eigenvectors that are constant on these parts. You just take an eigenvector for gamma, and you just copy the entry here, copy the entry here, and so on, double. The other eigenvectors, how are they going to be? They're going to be perpendicular on this part. So if you're perpendicular, you're going to be, you know, one is a negative of the other, and then that leads to this sign adjacency matrix. Here, let me give you a slightly different proof by this example. So let me write you down this adjacency matrix. Okay, I'm sorry, I'll put you through a lot more pain. So 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, and here will be the same, 0, 0, 1. Okay, so in general, what will happen when you do this signing of the adjacency matrix, let me erase here. What is it? Okay. Question? Which one? Where is it? Here? First row. A0 and C1. No. This is A of gamma prime. This is the original adjacency matrix. So I want to show you another way of looking at this adjacency matrix of this big graph. You can get the spectrum from these two. So I'll just want to show you a different way, okay, by this example. So what will happen in general that so gamma is my original graph, and gamma prime is the 2 cover, is the bigger graph. So the adjacency matrix of gamma prime will be something like this. You will have here, if you put the vertices of gamma times 0, it will be some matrix A1, here will be some matrix A2, it's a matrix, will be here some matrix A2, and here, what do you notice? A1, it's the same thing here. It's the same matrix here. So in general, that's what will happen. And what do you notice about this A1 and A2?
On the positive one,
okay, so if I put, so here, this is A1, this is A2, how much is A1 plus A2? A of A of gamma. And how much is A1 minus A2? AS. So based on this, you can do the thing that I mentioned earlier as follows. If you have A, so let me erase here. If I have A gamma U equals something like, let's say, some lambda times U, then I will do this thing about constant on the parts of the partition. So this implies that A of gamma prime times U will equals theta. This is exactly what I said about equitable partition. If I have an eigenvalue lambda here with U, I just put the values of U in all the parts of So if I had in the graph in A, if I had U1, I put U1 here. So okay. So that's one part. And then if I have a sign adjacency matrix times a V equals, let's say, theta times V, this is for a different eigenvalue for the sign adjacency matrix. Then I can do A gamma prime V minus V. These are going to be the vectors which are perpendicular on the parts, and this will give me also thank you, this is lambda, and this will be theta V minus V. This requires proof, so you have to prove this. This requires some kind of proof, and you can use this. Yeah, so you can use this to prove this fact. You see, like, if I have A gamma prime and I'm multiplying it by a vector UU, because the matrix is in this block form, what do I get? I get A1 plus A2U, A2 plus A1U. But what is A1 plus A2? It will be AU, or AU of gamma, so this is going to be lambda U. And the other one, if I have this other one, if I have A gamma prime times V minus V, this will be what? In my matrix I have A1, A2 meets, so it will be A1 minus A2 times V, and this other one will be A2 minus A1 V. But what is this? This will be ASV minus ASV. So this will give you theta. So you're lucky you just escaped one more exercise, but that's the proof. Okay? And then this will be because if you take a basis of eigenvectors here, then all the UU will be linearly independent. So you'll get half of the eigenvectors. If you take a basis of eigenvectors here, this will be linearly independent, and these ones and these ones will be orthogonal on each other. So you have the whole basis of eigenvectors. So that's the spectrum. Yeah.
How do we get lambda U and theta V will have match?
Sometimes you can have repeats. It does. It may happen, but my point is that from here, so from A, you will get n eigenvectors, and they will become these eigenvectors UU for the two-cover graph. Okay. These ones were a basis. These ones are linearly independent, so you're fine. So you got half of the spectrum. Then you go here. You don't care if theta is the same as lambda. You just play this game again. AS V is this. Then V minus V will be an eigenvector here. All the V, if you start here with the basis of eigenvectors for AS, all the V minus V's will be linearly independent. And anything from here will be linearly independent from anything from here because they're orthogonal. So this you have a basis of eigenvectors. So that's your spectrum, obviously including multiplicities, because you could have repeats in the lambda, you could have repeats in the thetas, you could have repeats between the two parts. So again, this is important to know because again, it's a different perspective, and you can say, well, what's a big deal? Well, this is a big deal because you have a question about matrices, is a question about graphs, and I'll show you tomorrow an application in the theory of expanders, which is very important, where people have used this connection to prove some big results. Now, for the result of Wang, he looked at this part. I have no doubt that he knew about two covers and so on, but it turns out that his construction of this sign adjacency matrix is equivalent to a two cover of the cube. And it turns out that that was studied in the 80s by people in finite geometry who wanted to, they wanted to look for two covers of n-dimensional cubes that do not contain C4. So you see, in the cube, you have many C4s. They're everywhere and so on. So people were looking at how can I lift the cube such that the n-dimensional cube such that it doesn't have any C4. And it turns out the cover that was in a paper in the mid 80s, it's the same sign adjacency matrix that, so after he proved this, people observed, well, by the way, this was here, but in this situation, people were looking at the finite geometry problem. They didn't consider, I don't know, they didn't look at this problem. So the moral of the story, it's important for you to look at different angles at the problem because you never know what may be useful. Okay, so I'll stop here for now. Okay, thank you.
Those is two covers and for it, like we have, for example, it is connected also.
Yeah, of course, you